Okay, good morning, everybody. So my talk is entitled Quebradona Treasures, a novel greenfields flash flotation test and development of geometrical relationships. And I do worry that I may have made myself something of a hostage to fortune by calling it Quebradona Treasures. I hope that you will get something, you will take something useful away from this. That's the aim. So to commence, a little bit of an outline of my talk. There's really three parts to the talk. The first part is just some background to the Quebradona project, because obviously it's a new project and I don't suppose too many people will know much about it yet. So where it is, what it is, and how it's going to be mined and processed. And that's by way of context to the second part of the talk, which is geometallurgical relationships that developed for Quebradona. And the key thing here really is the approach rather than the outcomes, although we'll certainly talk of the outcomes, but it's the approach that I think might be, because it's a little unusual, might turn out to be useful at other sites. So then we'll go on to the outcomes and then some questions that still remain to be answered. And lastly, flash flotation, why we considered it for Quebradona. But again, the interest really is perhaps more in the method that we developed. Again, hopefully it may be transferable to other operations, and then discuss the results. So moving into it, the location of the Quebradona project. The project is situated about 7 kilometers from the small town of Jericho in the department of Antioquia in Colombia. And Jericho is a beautiful little town. It was very strong traditions, very strong religious traditions, because it was the birthplace of Colombia's only Roman Catholic saint. It's also a coffee growing area, beautiful scenery, it's a holiday area. So it's environmentally and socially a very sensitive area. So absolutely key to the success of the project is social engagement, building up the support in the community, and of course, strict adherence to environmental requirements. We are helped by the fact that the mine is not actually visible from Jericho. It sits up behind this ridge up there, and there'll be very little, just really the ventilation shafts at the surface up here. The rest of the operations will be down in the valley, 1,000 meters below this mountain plateau. And this is a little bit of a sort of three-dimensional shot. You can see here the mine deposit in three-dimensional view, sitting about 400 meters below the ground surface at that point, with the deposit extending about 600 meters below that, which allows us to put the crushing plant underneath the deposit, so the ore reports by gravity, and then is then crushed and transported by conveyor about 6 kilometers, almost horizontally, out to daylight here, down in the valley. This valley floor, this is a very steep wall, about 1,000 meters high, and then the ground continues to slope on down at places around 25% slope down to the Cauca River below, a kilometer or so, a couple of kilometers away. So both the plant and the tailings disposal facility will be there. The tailings, because of the geography, the only possible method of disposing of tailings is stacking of filtered tailings, or dry stacking as it's often called. The other aspect is there's a lot of pyrite in the ore, which if we leave it in the flotation tailings would undoubtedly cause an acid drainage problem. So the pyrite is is floated off and goes into a separate pyrite residue, which is also filtered and stacked, but in sealed impoundments rather than just openly. Unfortunately, you probably can't see the resource and reserve statement. The initial resource was announced, the maiden resource was announced in 2014, and then it was updated in 2019 after the finishing of the PFS, the pre-feasibility study. And at the same time, we also announced a reserve at that stage, the maiden reserve. So the resource in 2019 was 602 million tons at 0.73% copper. The reserve is substantially smaller, 111 million tons, and that's the high-grade core that forms the basis of the current project. And that's a pretty good grade of copper, 1.25% copper, and 0.71 grams per ton of gold. So you can see that the gold is economically quite important to the project, although it's very much a copper mine. There's also silver, and there is moly. Later in the mine life, moly grades will go up, and moly is likely to become economic to recover, but it's not recovered in the initial project. The feasibility study is based on treating 6.2 million tons per annum over about 25 years. Turning to the geology and the drawing and leapfrog on the left here is a little view of the broad geology, and the current reserves are associated with this intrusion of early quartz diorite. And there is a cupola region up at the top there, which is exceptionally high in copper and surrounded by a shell of 1.25% copper. The shell isn't shown on here. The next shell out is the black shell here, which is 0.65% copper shell, and that basically encompasses the current project reserves. Then there's a green shell you may be able to see there, which is 0.45% copper. That encompasses the current resource. And then there is a large body, a very large body of low-grade mineralized material surrounded by the pink line there, 0.1% copper, which is not part of the current economic project at all. Over on the right here, we've got a view of the mine development. The grey is the tough ore that is going to be mined surrounding the diorite core in pink. And the key thing from this drawing is to see the very strong trend in copper grade, starting high at the top of the deposit and declining as we go deeper. That really dictated that we selected a top-down mining method. I guess the two methods that were really mostly under consideration were block caving or sub-level caving. Caving in general has high ore recovery and relatively low cost. But of course, block caving would have started at the top, bottom, or in the middle. With sub-level caving, we're able to start with the high-grade ore at the top. It's still possible that after a few years of sub-level caving, the project could convert to block caving. There is a disadvantage of sub-level caving method, and that is that it's quite inflexible. Once you've designed the mine and set it up, then you are locked into a sequence of delivery to the plant that cannot be changed, at least certainly not in any short-term way. And that does mean that the plant has to be capable of accepting essentially all of the variability that is thrown at it. And also, of course, financial planning is important. Since you can't change the ore to the plant, at least you need to understand what the results are going to be. Just a little on the sub-level cave to explain why it is basically an inflexible method. So mining proceeds along a linear front on each level, and that front moves across the ore body, and you have to do that, otherwise of course you get an unsafe situation developing or you lose ore. And you have 3 active mining levels at any one stage, with the advancing mine front staggered through the levels. That's when we get to full production. Initially, however, we'll of course start on just the first level. And because the tuff surrounds the diorite core, and we also have tuff in the dilution level above the main ore body, initially we're going to get some very high levels of tuff coming through. And as you'll see in a minute, that's important. So there will be days, not prolonged, but there will be days when we get up to 100% tuff ore early on, and between 50 and 100% in the early years, dropping to 0% towards the end of the mine life, and then rising again. A little bit about the mineralogy. These quite remarkable images really are prepared by the CSIRO in Perth using their Maya mapping tool. That's a high definition X-ray fluorescence mapping with sort of micron scale definition. And the sulfide mineralogy is quite simple. The copper is basically present as chalcopyrite. The remaining sulfur is present as pyrite. We have moly, but of course that only accounts for a very tiny amount of the sulfur. And you can see here that they tend to occur quite separately within the ore. In the top piece, which is higher grade, they're both tough. The top piece, which is higher grade, the copper is in very distinct veins in green. The The pyrite is in equally distinct veins in blue, and the moly is scattered through in red. But the copper also occurs not only in veins, but quite disseminated through the ore as well. If we look at the lower grade piece of ore at the bottom, we can see that the pyrite is still present predominantly in quite strong veins, but the copper veins have pretty much disappeared, and most of the copper is there disseminated. So it's a reasonable guess that that might influence recovery, with possibly higher recoveries in higher grade ore where the chalcopyrite is more vein related. And as we'll see later on, we do indeed have quite a strong relationship, relatively, with head grade and recovery. The process flow sheet. We call it conventional porphyry copper, but of course, as we all know, every ore is different and every flow sheet is therefore different. But it is fundamentally a porphyry copper type flow sheet. The primary crusher, gyratory underground, transporting the ore by 6 kilometers to a surface coarse ore stockpile with about 24 hours live capacity. From there, it goes to a secondary screen, the screen oversized to a secondary crusher, cone crusher. The screen undersized goes to a high pressure grinding roll feed stockpile. And then with selected high pressure grinding rolls, we'll come back and talk more about that. The product from the high pressure grinding rolls, a portion of it goes to a dry screen, which produces a fine ore stockpile, which is in essence an emergency stockpile for use when the crushing or HPGR system is down. The bulk of the HPGR product goes to these wet screens here. The wet screen undersize goes to primary cyclones, with 60% going to the mill, 40% going to flash float, and then of course the tail going back to the mill. The flash float concentrate reports directly to the regrind mill. The cyclone overflow reports to a bulk rougher float. Initially, we looked at selective flotation. We thought we would get better concentrate grades that way, but we found that in fact there was no advantage. But by going to a bulk float, that is floating the pyrite and the copper together, we had a simpler circuit and in fact slightly better recoveries, and we can still separate the copper and the pyrite effectively in the cleaner circuit. As we said earlier, we have to float the pyrite for environmental reasons, but also the pyrite is associated with gold, and by floating the pyrite and regrinding it, we can improve our gold recovery as well. The cleaner circuit is borrowing from a preferred circuit, which is a cleaner scalper column. At the moment, we're looking at the area style cavitation columns, external cavitation columns, so cleaner scalper column producing a high grade concentrate directly to final con. The tail from that goes to conventional scalpers, scavengers. The concentrate from those goes to a further cleaner column, and the tail from that goes to conventional scavengers again. Everything is pretty much in open circuit. The reason for that is because the fines in the ore accumulate if we close circuit, and that then rapidly reduces performance. So everything's in open circuit, even the conventional cleaner scavengers here, the concentrate is an open circuit. That does reduce the final concentrate grade, but it's important because the columns do not do such a good job of gold recovery. So we need the combination of columns and conventional cells to produce a good grade of concentrate balanced with the best possible gold recovery. And it's a very flexible circuit. So in practice, the operators can change the streams. They can recycle a stream if they need to. So it'll be very much an operational control to optimize that circuit and get the most economic balance at any time between recovery and concentrate grade. Everything gets thickened and filtered. The two tailing streams, the rougher tail and the pyrite, and of course, obviously the copper concentrate goes by truck to port. Moving on from there, and just going back, there are two conceptual studies I mentioned. There was a conceptual study which was required to support the announcement of the maiden resource back in 2014, and that was the focus of that study. There was a further conceptual study which started in 2015, finished 2016, and that was really to optimize the circuit. And that selected a sagged ball pebble crusher circuit. Advantage, of course, as I'm sure you all know, is generally that's a lower capital cost circuit. Lower operating costs in some respects, but with higher operating costs in terms of power, because it's a less power effective circuit compared with crushing type options. But hydroelectric power in Colombia is relatively low cost, which therefore makes the SAG ball circuit cost competitive. And it was based also on the fact that conceptual mine planning indicated a very stable ore feed containing about 30% tough ore. We got partway through the PFS, mid-2017, we received the mine planning, the PFS mine planning, and it showed that in fact the ore was going to be much more variable than we had anticipated, with, as I said earlier, the tough in early years between 50 and 100% and later down to 0%. The reason for that was simply that the tough is relatively high grade up the top and certainly economic to mine. So it was an economic decision to mine more of the tough. It was an advantage, but it did have a challenge for the plant design. And the test work showed comminution properties are highly variable, and some of the toughs among the hardest zone. Now, the graphs are a little bit hidden behind the picture here, but over on the right-hand side of this top graph here is the tough, with some of the tough being up to 95 to 97% on the SMC International Database. The dike is also itself very variable in hardness, ranging between about 20% on the database up to about 90%. So we have two different ore types with quite different hardness, and one of those ore types itself very variable. And that would have made a SAG ball circuit pretty well impossible to design. We would have had a very low degree of confidence in estimating the power required, and very, very difficult to operate. So while on paper the SAG circuit might show the best NPV, we realized that we wouldn't achieve that NPV because we wouldn't get the efficiencies in the plant. So that's why we changed to an HPGR ball and adopted really the circuit that we very successfully installed at Tropicana. And I noted before the fine ore stockpile. That's an important feature, having that fine ore stockpile, because it corrects the fact that very many of the HPGR plants, but at least ones with only one HPGR, suffered early on from very slow ramp-ups and poor availability. Having that stockpile of fine ore that can be fed directly to the mill has meant that Tropicana has achieved excellent productivity and has proved to be a very flexible circuit. So that's what we've adopted for Quebradona. Geomet program development. The development of the Geomet program at Quebradona has really been serendipitous. The question, and it's been successful. So the question, as I posed at the beginning, is could this approach be useful elsewhere? It arose because we had quite good test work for a conceptual study on composite samples from the 2014 study. So for the 2015 study, we didn't need to go back and repeat all that work. It was quite adequate for conceptual. So that gave us the opportunity to direct our metallurgical budget to studying 4 niche samples, which were selected together with the geologists to basically have a look at just get an understanding of just how variable the ore might be, and also to study gold deportment, because some of the early tests had quite poor gold recovery, saying gold's important. So we wanted to understand what we could potentially do to improve gold recovery. So we selected 4 niche samples, and we found that the chemistry and metallurgy were very variable. And so the question arose, was the chemistry related to the metallurgy? In the top right-hand corner, I think you can see there's obviously not very many points. There's 4 points basically, plus a couple of extras from earlier work. But the dike bondwork index pretty much tracked the potassium content, and the tough bondwork index 2 points only, but it was noticeable that those 2 points had very, very different ratios of sulfur to copper. In other words, the ratio of the ore of the pyrite to chalcopyrite was very, very different. Not a lot of data, but it did prompt us to look at the ore body and realize that the potassium trend was very strong, rising potassium in dike steadily rising to the bottom of the ore body, rising with depth, while the reverse happened with the sulfur copper ratio in the tuff. The sulfur copper ratio is high at the top. In other words, a lot of pyrite at the top of the ore body, declining to very little pyrite indeed towards the end of the mine life. So that gave us some encouragement that perhaps the trends might be real. They may mean something. So in the pre-feasibility study, we selected 10 samples of tuff and 10 samples of dike. And the composites were based on chemistry, not on location. In fact, the composites contained core from different locations in a single composite. The aim being that each composite would be relatively homogeneous chemistry, but with the composites being very different to one another. And we considered a range of elements. We didn't just consider the sulfur, copper, and potassium, because obviously that was just an observation. We considered a range of elements that we'd noted varied between the different samples. And in fact, we did get a wide range of properties, both flotation and comminution, but focusing for the moment on the comminution just to follow that story through. For the dike and the tuff, the bondwork index actually tracked pretty well just purely the magnesium with an R squared of 0.75. And separating out the bondwork index for the dike alone, we could get a very strong relationship with an R squared of 0.93 using calcium, magnesium, phosphorus, and vanadium. Drop weight index, we didn't have enough data to separate out the different ore types, so we could only fit the total ore, but we still got a very good R squared of 0.91 fitted with silver and gold, magnesium, sodium, and vanadium, and you can't see all of the graphs there. All of these relationships are statistically highly significant. So for the FS, we were in a position where the geological database for Quebradona includes multi-element ICP scans on every single 2-meter drill intercept that is drilled and assayed. So we were able to use the relationships that we developed in the PFS to predict the drop weight index, the bondwork index, and also copper and gold recoveries and sulfur recoveries for every single intercept within the mine footprint. And that's a total of 4,500 intercepts. And we found that the bondwork indices were pretty much all in the expected range. That doesn't prove they're right, of course, but they all made good sense, pretty much all. But the drop weight index, a lot made sense, but a proportion of them were way too high or way too low. And we had 10 to 20% of the samples showing drop weight indices that did not seem realistic. So for the FS, we again took, in this case, 12 tuff and 12 dike composites, but we prepared them from drill core, which we predicted from the PFS relationships to have extreme or unlikely properties. So it was really a worst case. And the aim, obviously, was to improve the relationships, to improve the validity and robustness of the relationships. We were able this time to prepare the samples from contiguous core because we found that the predicted properties were quite persistent over length of core, at least 10 meters, which was enough for the planned test program. The results were highly scattered, and on the right-hand side here, you can see, I think, part of the graph there. The tuff points are in orange, the dike points are in blue, and the red line here is actually the highest drop weight index that we measured in the PFS work, 10.6. And most of the tuff results were, in fact, the majority of them were above that line. So quite a lot of the tuff drop weight indexes were higher than the highest previous measurement we got. So we fitted new relationships to that data, including the PFS data, of course, the combined data. And we found that the tuff drop weight index basically correlated just with gold, with a correlation coefficient R squared 0.88, a very simple relationship. For the dike, a more complex relationship, not quite as good at R squared, but still very acceptable, 0.77, and an equation including magnesium and a couple other things as well. But we had an opportunity to validate the relationship, because as you're aware, piloting of high pressure grinding rolls is currently essential. There's no small scale technique accepted for sizing grinding rolls, unlike obviously bondwork index for ball mills. So we'd used about 9 tons of specially drilled large diameter drill core, which turned out to be close to the ore body average drop weight index of 9.7 kilowatt hours per cubic meter. We'd actually hoped it would be a little harder because most of the core went through the upper tuff, which we knew to be generally harder, but we couldn't really predict the hardness of the large diameter core because we only had approximate assays based on holes nearby. So as I say, we ended up with something that was good. It was average, but it wasn't quite as hard as we'd like. So we did an additional program where we targeted some core, which we wanted to be around about the design or the 85th percentile drop weight index for the ore body of 11.6. So we selected quarter core for testing. Quarter core not ideal for HPGR testing, but we were able to make it work with great care with the sample preparation, and it had the benefit that we had the assays on the half core that had gone for analysis, so we were able to predict the drop weight index to make sure that we got what we set out to get. We actually did check Schmidt-Hammer and Equitip as well, but found we had a certain number of lengths of core where we had some drop weight index data, either on immediately adjacent intercepts or the same intercepts. So we were able to see that, in fact, the geochemistry was the strongest predictor. So we prepared the samples, they went off for testing. We hedged our bets a little. We prepared in 2 groups, group 1 and group 2, with group 1 being expected to be harder and group 2 just a little softer. And in fact, for group 1, we got measured 11.9 versus predicted 11.8. And that's correct, 11.8 and 11.9. The figures are missing from the screen, unfortunately. And for group 2, we got predicted 11.4 and measured 11.0. So on average, we hit pretty close on the 11.6 that we were aiming for. So that was a strong validation of the validity of our whole approach. Turning to the sizing of the high pressure grinding rolls, as I've said, they require piloting, but of course in the PFS we didn't have piloting. So for the PFS, we did use the drop weight index derived index MIH to evaluate the HPGR. We also evaluated against benchmarking with Boddington being a particularly important benchmark because it's a very highly competent ore, much like the Quebradona tuff. And so because of that, we were interested to see how our method of prediction using MIH actually compared to the pilot plant work. We'd also sent samples off for piston and die test to Canada as well. You can see on the graph here on the bottom left-hand corner, there's 2 points here where the predicted and the operating MIH, we compared by looking at the operating MIH, much like an operating bondwork index. And you can see good correlation in the sort of mid-range ore. But once we move to the harder ore, absolutely no correlation whatsoever. The operating bondwork index stays largely constant while the test MIH steadily increases. We also compared with the piston and die, and again, unfortunately, you can't see the numbers very well here, but it was completely scattered. There was no relationship between the piston and die predicted energy and the operating energy based on MIH. For the ball mill, obviously bondwork index being the basis for design. For the tuff, that was our poorest fit, in fact, but even then we achieved 0.61 R squared using aluminium, silver and copper. And that was the more difficult one to fit. But the problem really is that measured values on tuff greater than 20 can't be predicted. Softer values actually predict quite well, but above 20, the prediction just, we can't find anything that predicts those values. But it's an interesting question whether that's actually a problem with the bondwork index test results or a problem with the prediction, because of course above 20, the bondwork index test itself becomes somewhat lower confidence in it. So we don't, so it's possible in fact to say the prediction is the better guide. For recovery, just referring to recovery, copper and sulfur have a direct influence on copper recovery and grade, but for these other elements of the hardness, we're not suggesting, of course, that the elements directly control the hardness. They're just indicators of differences in the degree of alteration and the type of alteration, which in turn then affect the physical properties of the ore. Flotation design parameters, we've been focusing a lot on comminution, but we certainly did work on flotation as well. And there we found actually there was no benefit in separating out the tuff and the dike ore. It seems that the flotation response is much more related to the degree of alteration. In other words, in particular, the copper, the gold, etc., rather than the host ore, the host rock. So for the flotation design parameters, generally we got benefits by breaking the data into head grade groups. So for copper recovery, a group less than 1% copper head grade and a group greater than 1% copper head grade. And in both cases, copper is one of the elements, of course, as we expect, that predicts recovery, but helped with sulfur in the case of the lower grade material, aluminium, phosphorus, and cerium in the case of the higher grade material, and some very good R-squared. Concentrate grade, not as accurately predicted in the lower grade head grade, but actually that's not terribly important because we never really treat an average grade into the plant less than 1% copper, but of course for modeling purposes it's useful, it's important. And greater than 1% copper, we've got R-squared 0.82 with silver, chromium, and sodium. We're also able to predict not just the pyrite recovery, but the pyrite recovery to the copper concentrate, as well as the pyrite residue grade. And those are important because with those, we can predict the rougher mass pull and the mass going to the pyrite residue. So just to talk about that a little bit more, the rougher mass pull is important for design. It dictates the size of the regrind mill, the size of the cleaner circuit, the thickeners, and the filtration, because of course this plant could as well be limited by filtration capacity as it is by grinding capacity. We are constrained in a sense at both ends because we have to produce a material suitable for stacking in the tailings dam. So the pyrite residue mass is also important for filtration. We tried to predict the rougher mass by predicting silicate gangue recovery, and we could do that. We could predict silicate gangue recovery quite accurately, but the errors tend to accumulate and lead to some unrealistic predictions. So we found the best procedure was to estimate copper recovery and concentrate grade. We've talked about that. Estimate pyrite recovery and pyrite residue grade, taking the pyrite recovery actually as a fixed 98% because it varies very little. Estimate how much pyrite is recovered to the copper concentrate, and thus we can estimate the rougher mass pull and the pyrite residue mass. And it's interesting, the graph here shows the pyrite recovery versus the pyrite over copper head grade, and it's about a 0.3 R-squared. So there's a relationship there, not so strong, but there is a relationship. And then over here, we also find that the pyrite recovery to copper is related to the moly head grade. Obviously strongly controlled by this one point here, but still a general trend is there. And that's interesting because it does suggest that perhaps in moly-rich zones, the pyrite might be harder to depress. So we get a combined relationship, pyrite copper and with the pyrite copper and the moly, with a combined R-squared of 0.73. The we also need to predict the plant performance from the mine schedule predictions, and the mine schedule can currently only report monthly grades for the main economic elements, and only for the total mill feed. It can report tuff and dike separately in mass, but not information on them. We are working at incorporating the geometallurgical relationships into the block model, and then hopefully through that, of course, more information coming through the mine schedule. But it's not so easy with caving, because you've also got to model the cave flow and the mixing in the cave. However, we're actually able to come up with some quite useful relationships just with the available data. So here we're not separating out the dike and the tuff, the diorite and the tuff. You can see on the right here, we've got quite a strong relationship between copper recovery and actually the log of the copper head grade. The red points being the diorite, the orange, the tuff, so you can see there's really not any significant difference between them. To fit that curve, we have to break it into head grade regions, because there's no mathematical function that fits that curve. So above 4% copper, we take it constant 99%, and then we have 0.4 to 0.8, 0.65 R squared, and then less than 0.8% copper. And the copper concentrate, above 2%, we just say it's a constant 30, and less than 2%, we have a relationship, not such a strong one. But nonetheless, these relationships, even where they're not so strong, are still much better for financial planning than just simply using an average through the life of mine. And quite a good relationship predicting pyrite in residue and gold recovery, not such good, but again, useful. So in conclusion on the geometallurgy, all of the key metallurgical design parameters for the Quebradona project can be very well predicted from geochemistry. The method of sample selection, testing a wide range of geochemistry, may have made it easier to identify the relationships. The relationships developed for predicting recoveries and grades in the mine schedule are probably related to the degree of alteration reflected in the head grade. And although the SMC high pressure grinding roll power index can be predicted, this doesn't correlate with the pilot testing power draw. So this is an area for further work. Is it possible to develop some useful relationships directly with the geochemistry? Okay, so turning now to flash flotation. Gold will contribute close to 25% of revenue at Quebradona, despite the moderately low recovery of about 61%. The gold recovery to the bulk rougher concentrate is close to 90%. There's not a lot of gravity recoverable gold, but 20 to 30% of the gold is free gold, but it's fine grained. It's in the 20 micron range, but that recovers very well, and with recoveries up in the high 90s. But gold is easily lost, as you can see, because we've got a very high recovery in the rougher, but not so high in final. So flash flotation may capture some gold before the surfaces deteriorate. For greenfield sites, Imtech recommend evaluating values recovered in the first 2 minutes, but the trouble is that demonstrates that flash flotation will work, but not that it will improve recovery. It's possible to do a coarse batch grind, scalp off the 600 micron material to protect the mechanism and float the finer, but that doesn't simulate the effective closed circuit grinding on the flash feed mineralogy and particle size. So we developed a test procedure around a batch classifier using the same principle as beaker decantation, and using a classifier we'd actually built for some work on here, its hydrofloat technique. Here's a picture of the classifier. It's basically a piece of 150 millimeter diameter PVC tube with some valves attached, valves top and bottom, and one around about a third of the way up, a little bit less than a third of the way up. So in operation, we pour the ground material into the tube. We close the top and bottom valves. We invert the tube multiple times vigorously to thoroughly mix, and that's a critical factor. Then you settle, very short settling times, which is why we have to use a tube, because we're settling at a reasonably coarse size. Once you settle for the required time, you close the lower valve there, the middle valve, and then you're able to discharge the coarse material from the bottom section, the fine material from the top section. We only did a single separation step because we wanted to simulate the not perfect classification with the cyclone. And in fact, we got pretty good results with that. So the flow sheet, grind 2 kilogram charge, or 1/3 of the time required for a P80 of 106, settle it in the tube. The coarse fraction goes to a benchtop cell, remove the +600, float it, recombine the +600 with the tails, make up the weight, and go back to the grinding step for the next stage. The fines, meanwhile, we accumulate together over 4 cycles to make up sufficient for the fines flotation. And there are four cycles in this. It make up a single fines float, and then we did a further 4 cycles. We separated it like that to get some sort of check on reproducibility and also to track how much things changed with time. So you can see here there is a change in the grind time through the cycles, and I guess even by the end of cycle 8 we weren't completely stable, but still the operators, it's a little bit uneven because of course the operators are looking at the size of the overflow and then adjusting the grind time accordingly and gradually homing in on about the target grind size. So we weren't too far off. If you look at the recovery and grade recovery curve through the cycles, you can see in cycle 1 a very different curve to the rest of the cycles for copper. So the big change happened after the first cycle, but no real trend through here. But even so, the last cycle is a little bit over to the left of the other cycles. But for sulfur, it's a bit different for pyrite because the pyrite is both dense and very resistant to grinding. So it's actually the second cycle that had the strongest grade recovery relationship, and then it does step pretty much in order through the cycles, with the last cycle being over the left here. So we weren't completely stable through cycles 5 to 8, but we were reasonably stable and were able to calculate an overall mass balance and materials balance from that data, which we put into LIM as an easier way to handle the data and present it. That also allowed us to look directly at a model where we directly followed the experimental work with 100% of the classifier underflow going to the flash float, but also to use the same data to model where it was a 60-40 split as it would be in the plant. This is not a particle size-based model. The mill is just simply a pass-through device. We didn't have enough information to model on a size-by-size basis, but it is a kinetic-based model. So allowing for 40% of the underflow treated in the plant, this predicts 45% copper recovery, 36% gold recovery, and 38% pyrite recovery. But the other notable thing here is the extremely high circulating load of pyrite, over 1400% circulating load, because this is based on 100 units of new feed, compared with 428 for 30% of gangue circulating load. So the pyrite is very high accumulation, and that was with, we did get some pyrite recovered in the flash float, about 38%, and that's with a selective pyrite float. So in reality in the plant, if we were to add xanthate to the mill and aim to recover some pyrite in the flash float, another advantage of the flash float is we could probably pull out quite a lot of pyrite early on and reduce that big circulating load, about nearly 700 tons of pyrite circulating for a 769 ton an hour new feed. In terms of predicting the benefits of flash, we got, comparing with 3 baseline tests, triplicated baseline tests, we got a 0.9% increase in gold recovery. Now, obviously, there's a wide error margin on that, and we wouldn't swear to that 0.9%. But considering the strong copper and gold recovery achieved in flash flotation and comparing that to published data or industrial benchmarking, there's no doubt that installation of flash flotation is justified for the Quebradona plant. So future improvements, because this was a first attempt and it's worth commenting on where I think we could improve it. It would be much easier if we built the classifier from transparent PVC. The hardest part of setting the method up was getting the mixing right. We couldn't get stable results. It turned out to be to do with mixing, and it would have been much easier if we could have seen what was going on. The valves were very hard to operate, a small practical issue, but actually quite a challenge. So look at what sort of valves to use next time. Flow defines each cycle. The kinetics was much slower in the fines flotation compared with the batch tests on fresh ore. So probably aging had an effect, and in fact, therefore our recovery improvements are probably underestimated. Increase the number of cycles to make sure that it's stable. And also we intended to do, but unfortunately weren't able to, do size analyses on the flash float concentrate, because that's important for the regrind mill sizing, and preferably sized by assay on all final cycle products to get a better understanding of the performance of the flotation. And of course, ideally, if a budget allowed, replicate the whole thing. So that's it. Thank you very much. I think I've run a little over time, I'm sorry.
No, Nick, that's perfect. Thank you. It was a really interesting talk, and summarizes a huge amount of work that you've put into the project there. So thank you for sharing that with us. The time is perfect. We've got 10 minutes for questions. So for those of you online, please feel free to ask questions in the Q&A box, and we'll post those over to Nick as they come in. So yeah, so thank you again, Nick. We have already got one question from Sean Baker, just asking if you could elaborate a little bit more on some of the techniques that you've used to interrogate the geochemical relationships. Did you do them manually in Excel, or do you have supporting software to help make those correlations and predictions?
Yes, well, we don't have a fancy software package, but most of the work really was done in Excel. But to produce the pretty graphs with the confidence limits and so on, use an Excel add-in called Analyze It, which is relatively inexpensive. And because it's Excel-based, it's quite easy to use. So certainly I've used that. But really, it did use principal components a little bit just to help identify the elements are useful. But honestly, mostly it's trial and error.
Okay, thank you very much for that. Just one question, just to follow on. Did you have you managed to incorporate much mineralogy, or is that something that would be done down the track?
Mineralogy into the geometallurgy, not really. We've done mineralogy. We've done some MLA work and some optical mineralogy, and of course the work by CSRO as well. You know, so we've got a reasonable amount of mineralogy, but no, we haven't directly linked that to the geometallurgy.
Rick, did you want to go ahead and ask your question?
Sure. Yeah. Thanks, Nathan. I think it's sort of a little bit related to that question in that you know, you reported quite a variation in I guess characteristics based on different rock types like the tuff, so I was just interested to know, when you were doing the geochemical testing, whether you're taking into account rock type, texture, vein density, the sort of the other, I guess, rock-based, texture-based measures that might be helping to improve the correlations.
In this case, no. I mean, for Gramology, with a completely different project, different issue, but there, yes, we used hyperspectral data, we used logging data and everything else. I guess being metallurgists, we find it easier to work with chemical data than hyperspectral data is great, but it is a little harder to work with the features. And of course, geological log data tends to be a little more difficult because while it tries to be quantitative, I guess it is still somewhat more subject to personal variability. So I suppose if we can get the answers we want using the geochemistry, it's a very simple and straightforward process. If we hadn't achieved that, well, then obviously our next step is certainly to look particularly at the hyperspectral data, which of course we're very interested in. But in this case, we got such good relationships with the chemistry, we didn't really progress. I guess a couple of things like the tough Bondwick index, it could be interesting to look and see if those very hard samples, whether there could be anything in the geology that would help us to predict those. That's certainly something that would be interesting to have a look at.
The published work on the deposit kind of conforms to a classic porphyry alteration model. Why is the tuff so hard? Do you know much about why it's, which part of the alteration zone it intercepts as to why it's so prohibitively hard?
Well, I'm probably not the right person to ask that. I mean, of course, we've had some discussions on it very early on, because tuff, volcanic ash, it should actually be soft. And indeed, if you look at the tuff out near the mouth of the tunnel, well away from the alteration zone, it is. It's almost soil-like, So clearly, it's the alteration that has made the tuff hard, which then makes it slightly puzzling that the low gold grades correlate with the hardest tuff. So I think the honest answer is to say we don't have an answer on that yet, and our geologists are certainly have been very interested. Of course, I guess all of these relationships have mostly been developed by metallurgists, but we're working closely with the geologists, and they're keen actually to take all this work further, of course, and do more work on what the different element correlations might mean in terms of mineralogy and gangue mineralogy. So I think you could say that's an ongoing study, but not something we have an answer to at the moment. Sure.
Okay, excellent. Thank you. So there's a few questions. Nick, I don't know whether you want to open up the question answer box and you can look at these as well, but there's a few coming through from Michael Young. Probably a few more specifics on some of the grain sizes of the chalcopyrite and the pyrite and primary grind size and the regrind size. I don't know whether you want to reel off that information now. Feel free if you do. And then Michael also had a follow-on question which was related to the HPGR, if you wanted to compare that to a tower mill circuit instead of a ball mill.
Okay, so the question is the grain size?
Chalcopyrite grain size and the pyrite grain size.
Yes. I guess most of the mineralogy, of course, is done in fact on ground material. So it's always difficult to. I don't think can't bring to mind much information on the grain size in the ore, although of course the Maya mapping certainly there's the ability to interrogate that data to do some of that, and I have to say we haven't done that yet. But in terms of the grinding, it's a reasonably coarse grind. In the conceptual study, we went for a 106 micron grind. We looked at coarsening that. The indications were that the dike, we could easily go to 150. The tuff needed to be ground to 106 and would even give better recoveries down at 75 or even 38 microns. But then when we went to, that was in a selective float. When we went to bulk floating, where of course, if there are pyrite, chalcopyrite composites, we're floating them together and then regrinding them, that allowed us to coarsen the grind size to 150 microns and achieve good recovery from the tuff and the dike at 150. If we go up to 212, we start to see a real fall off in performance. So the liberation size, if you like, is somewhere in the range 150 to 212 microns, with 150 being the economic optimum. I mean, I guess we haven't tested 160, 170, but looking at the curves, 150 is the economic optimum. The regrind size, we go quite fine, and indeed that's been something that's had quite a lot of challenges to it. Have we got the right regrind size? So we're grinding down to 25 microns, and that's really just grade recovery response related. That's just where our economic optimum is. And I think there was a third part to the question.
There was a third part that was related to Louise and did you look at HPGR to tower mill circuit instead of a ball mill to increase grinding efficiency by using smaller grinding medium?
No, we didn't. We hadn't really looked at grinding media in that context. The driver for going to HPGR was really totally the variability in the ore hardness, and the fact that our very good experience with HPGR at Tropicana has convinced us that that's a very stable circuit, and that was the driver. I'm not sure if that answers the question.
I hope so. I think that's good. Thank you. Yeah. We have a kind of comment and a question here from Tim Napier-Munn, who says it's good, long time no see, Nick, so I was pleased to hear from you. And commenting on obviously a very nice case study Could you comment a little bit more? He was pleased to see that the grade recovery were well predicted from assays, and noticing that you include confidence intervals on some of the models, which is a good thing to do. Could you use the calculated uncertainties in the models in any formal way as part of planning, or just to give a general idea of the reliability of these predictions?
I'm not sure I can directly answer that, but what I can say is for economic purposes, we don't take the mean result. We actually take the 75th or 85th percentile of the predictions for economic, for justifying the project. Obviously, when we look at the, when we look through the period of the project at the trends, then of course we use the, we use the actual trends. But when we look at justifying the project, we don't look at the mean, we look at the 75th or 85th percentile. I'm not sure if that answers the question.
Okay, I have to say I'm not too sure either, but we can check back with Tim to see if that's satisfied his curiosity there. So Sam, we do have a few more questions online. Rocio, a PhD student here at the BRC, was just asking if you could get any insights on the chemistry and therefore the therefore mineralogy that was affecting the results of the bond work index and the HPGR test results, considering the different sample top size tested in each test.
Any insights as to how the chemistry is affecting, or are we referring here to the?
I think we might be going back towards the mineralogical linkages there to sort of say, but from the chemistry, can you make some inferences on the mineralogical controls that were affecting?
Oh, okay. Well, the answer to that is yes. We've had a very preliminary look. The geologists have commented, and I didn't cover that, but the geologists have certainly covered that a little bit in terms of what the different elements may indicate about where we are on the scale of alteration types. So to that extent, we've done that. But have we related that directly in any more formal way to the mineralogy? No, not yet. As I was saying earlier, that area of trying to get a better understanding of what this is all telling us mineralogically is work still to do. Yeah,
of course. Okay, we are just about out of time. There are a couple of extra questions, and perhaps one of the key ones here would just be: has the flash test procedure been used on other projects, or do you intend to use it on other projects in the future? Is it something that you're going to maintain with AGA?
Well, I'm not sure whether AGA has got any other projects. Talking for AGA for a second, what I can say is that certainly Peter Burke at Imtech has been quite interested in the procedure, and I think he has passed it on to at least one other company and maybe more than one. So certainly he seems to think that it's a useful improvement, it's a useful addition to the toolbox. So yeah, I hope it'll be used. I mean, the equipment, it's quite a time-consuming procedure, of course, but the equipment is not expensive or difficult to build. And really, the procedure worked out pretty well. So I'd like to think it'll be used some more.
Is it universally applicable to all deposit types, or do you see there's like a niche deposit type that you could see early on where you may want to implement the test and also the flash flotation procedure?
That's a very good question. Where is flash flotation applicable? I think where the published data shows that flash flotation has been pretty well universally useful is where you have gold flotation. If it's pure copper, I'm not sure the evidence in favor of flash flotation is necessarily so strong, but where you're relying on flotation to recover gold pyrite, I think if you look at the published papers, you can see that generally gold recovery has benefited by several percent generally from flash flotation. So I think if it was me, if I was looking for Grammalotti, we've looked at flash flotation as well. So for me, if I was looking at flotation for any kind of gold deposit, I'd certainly be looking at flash. And I think that would be a view quite widely reflected in AGA.